Now, the motivation to study learning, of course, came from machine learning, from the success of a deep learning and from the things that I've observed. But then that one feature, understanding how learning works, was the key concept that should be introduced into the dynamics of the universe, that enabled me to actually view the entire world from the microscopic to macroscopic scales as a unified system. But now imagine that we have the new type of variables, and when they change, they actually modify the law. They modify the actual laws of physics. Now, very strange. That's not something we are used to in physics. They are also pretty well known in biology, although we don't call them as trainable variables. Your genotype, right? So this is something that the organisms evolve and change, and then those variables stay in the future generations.
Hello, everybody, and welcome back to Chasing Consciousness. So today we have the fascinating possibility that the world is like a neural network to consider. Now, on the show in Series 2, we deeply considered the way in which particles and sometimes even minds seem to be interconnected in the universe, even beyond the apparent causal links of space and time. We also covered the brain science of neuroplasticity in Series 1, if any listeners want to go back and understand how that works. Now, applying the idea of neuroplasticity to the universe, that in some way the dynamic evolution of systems in the universe adapt depending on the requirements, could explain some of the extraordinary fine-tuning we seem to see that permitted the arising of life in the first place. And along the way, it could potentially fix some of the other biggest gaps of disagreement between our best theories of physics. Now, our guest today, the Russian physicist Vitaly Vanchurin, has not only developed this theory from the ground up, but he's connecting it with biological systems and even developing a new type of computer processor to model it. Now, after many years at the University of Minnesota, he's taken a position at the National Institute of Health and has more or less simultaneously launched a new company, Artificial Neural Computing, that connects physics, biology, and machine learning. Now, ever since I first heard about this theory, I've been gagging to speak to Professor Vanchurin, and the extent to which this is just an analogy or in fact a real claim about the universe remains to be answered. So I simply can't wait to get into this. So without further ado, let's go. Vitaly Vanchurin, welcome to Chasing Consciousness. Thank you so much for joining us. Welcome. How are you?
Good. Thank you. Thank you for having me.
It's a great pleasure. So to remind the listeners that scientists aren't just data crunching machines, but people who, like us, were once kids with innocence about the world, I love to start by asking my guests about the first big questions that came up for you when you started reflecting about the nature of existence and the world sometime, I don't know, 8, 9, 10, 11. What can you remember from that time that really stayed with you?
Yeah, there were questions that I couldn't answer. I wanted to answer really badly, and there was questions, as I recall, about infinity. So somebody, I don't know, maybe my older brother or somebody told me about the infinity, and I tried to imagine it, and I failed. So, and I started thinking about this more, and then I realized that's not only something very big that I cannot understand, but also something very small. It was kind of a related problem. And at that point, I think, I was absolutely sure that this question should have an answer. I just don't know the right tools to answer that. And maybe that's the time when I was already shaping my mind as a scientist. Okay, if you have a question you cannot answer, well, what do? Go look for tools, mathematical tools. that in my case it would have been mathematical tools, and then by doing that, I think I eventually came up with a picture where it was satisfactory for myself. But yeah, the first questions, they were all about math. I think I was also always a math person to start with.
Maybe it's the language of the world,
That's what I think. That's what I'll try to argue.
So before we get into artificial neural networks and your attempts to try and resolve some of the biggest inconsistencies still open in physics, let's get down to the main topic for today's discussion, which is this world as a neural network. Now, we are amateurs, so Vitaly, if you can, without getting too mathematical, but also not brushing over any of the crucial concepts, because we do also have quite an advanced audience. Tell us the main ideas and the steps that brought you to this extraordinary idea.
Right. So yeah, I think we're all amateurs here, including myself, and yeah, I'll try to explain you the motivations and how I came to this idea, but whether this is a right idea or wrong idea, I want to right away say that remains to be seen. So let's not put too much pressure, like I'm proving something here. Okay, but yes. So what is it important in this new paradigm? What is one thing that differs from the other constructions? Again, what is that new tool that I would want to introduce? I figured out that I need to introduce in order to study the universe as a neural network. And that one tool was learning. So that was thing that kind of we all experience in life. We learn, and we kind of, you learn better, you get better grades. But I wanted to have a more precise definition of what that means. Now, the motivation to study learning, of course, came from machine learning, from the success of a deep learning, and from the things that I've observed. But then that one feature, understanding how learning works, was the key concept that should be introduced into the dynamics of the universe, that enabled me to actually view the entire world from the microscopic to macroscopic scales as a unified system. And it does, in some limits, have a behavior as if learning is not important. Maybe on the physical scales, where we were pretty good in developing physical theories without digging too much into concepts of learning. But as you go to bigger and bigger scales, especially when you start including observers like us, macroscopic observers, I think that was the missing piece in the puzzle. And so realizing that little piece can be mathematically modeled, explained, and controlled, then I was very much tempted to see, okay, well, if I have that mathematics, how can I apply it to the universe, and what kind of modifications to the usual picture of the universe will it bring? So to go back to your question, originally just understanding machine learning was my main motivation. How does it work? When does it work? And when it doesn't work, what makes it work better? And then once I convinced myself that I think I have a good understanding of that, now let's take that and apply it to the universe. Of course, that step is least trivial, but nevertheless, I think that was the crucial step. Now, when I say learning, it seems again abstract, but once you consider learning in the context of neural networks, say artificial neural networks, then it has a precise meaning. It has precise visualization, the type of dynamics that gives that learning. And so, as a physicist, if you see something that is defined precisely, then you're in business. Then you can take it and say, all right, so now let's model the universe with this one additional piece. So that's that. Without going into details, that would have been my answer to the question: what was new for me. Now, actually, when I do speak about this with other people, the other people find other things that are new to them. But for me, this one concept of actually having a well-defined definition, well-defined mathematical structure that represents this new type of dynamics was the crucial step.
So this theory of learning is not so much about you're saying that in some sense the way that the universe evolves is similar to the way in which a neural network learns. Is that the basic idea?
I would just actually put an equal sign, not similar, but in your model you make an assumption that this is exactly how universe works. So you write down exactly the same equations. And then the question, of course, you do not see that microscopical learning happening on all scales, and on larger scales, you see this learning have different representation. And so maybe on one scale, it is represented as quantum mechanics. On the other scale, it may be represented as general relativity. And there are many different scales on which this learning dynamics would be represented differently.
So, Vitaly, are you suggesting that the evolution of the world is in some sense the world learning over time?
Oh, absolutely. Yeah. So, I mean, I know it's a crazy idea. So with my physicist hat on, it is not how we view the universe. It's not how we view the laws of physics. And so if I am to actually show that this idea actually makes sense, I cannot just say, I think universe is learning. So that's not good enough. So what you should do is start with that concept and then show how all of the standard physics emerge from that in certain limits. And so, but at the end of the day, you're absolutely right. I am suggesting that this entire universe is just learning, yeah.
But then that leads us towards a kind of cosmic consciousness model, because there must be some repository in which this learning is held. I mean, obviously memory is a big word and it's not something that we understand even in neural networks, but in some sense, there must be a repository in which that learning is held, which does bring us to a cosmic consciousness model. Right. How do you feel about that? Does it feel strange as a physicist thinking that the universe itself could have some kind of total cosmic consciousness?
So for me as a physicist, if there is a word that I cannot define, I don't have to think about it. So for most physicists, you ask what is consciousness, they will fail to define it and say, well, too bad, I don't have to think about this. Now, however, I think with this concept of learning, there is a good definition of consciousness. And with this respect, everything is conscious, including my coffee mug here, right here. And I'll give you this definition. So this a definition of consciousness within this concept of a learning theory of neural network. What seems to look like a consciousness is the efficiency of learning. So if a given subsystem is very good in learning its environment, then it is more conscious. If it's very bad, it doesn't change much, it's already maybe learned everything it could, then it doesn't have a great degree of consciousness. Now, that's a definition of consciousness. Now, whether this is the only one and with this you can do calculations and then look at different systems and say, well, look like a human has a bigger consciousness than a coffee mug or a cell phone, but and then you can do comparison, and you can think about the consciousness meter like a thermometer. You can really stuck it into some subsystem and say, all right, well, give me the number, tell me how conscious this piece of metal is, or how conscious this organism is, or maybe a group of organisms is. And that's possible once you have defined it. Now, before you defined it, it is something that we think we know, we think we feel what it is, but it's hard for us to actually put a finger and say, no, this is what it is. But the reason I do want to talk, and I can talk about consciousness, is because I think that I've identified this one thing. It may be wrong, it may have to be modified, but at least it's a definition of consciousness, and has to do with the efficiency of learning, in my opinion. But then everything is every subsystem has some consciousness, and there is also this, global consciousness. This whole universe that is, if it is learning, has all of its parts, and the parts are learning as well. Just like we have parts, we have cells, and they are learning as well. But we as an organism have a bigger consciousness as the consciousness of individual cells, because we are able to actually use their consciousness, their effectiveness of learning, to be even a better learner. And that is what makes us better and more. Now, whether we are the most optimal ones, or I don't think so, there is room to improve. But with this respect, now, if you think of the entire universe, with all of this, organisms and all of the pieces that make it, then that consciousness is a lot more efficient to learn. It's like the super consciousness, the most you can get of that. So it's kind of a super observer in the sense of a physics, but would be a super conscious observer, because it's really, really good in learning.
Well, we're definitely going to come back to observers, because that's one of the big ones. That's it's an open book in quantum mechanics. But the big question here, which I've been itching to ask all day, actually, is the world as a neural network an analogy, or do you really think that the world could actually be a neural network?
Yeah, so there is a fine border between the two, right? So now it turns out that if you just take it as a model, then as a model, it provides a very good description to the world around us. And if at some point I will see that this model fails, there is some phenomena, maybe macroscopic, maybe microscopic, where this conception doesn't quite fit, then this model would have to be modified. And then at that time, I would say, well, it was just a model. And we know in physics, every model you make, there is always, a century later, there's a better model that can make it that works even better. So if it is just a model, then this is just a convenient and nice way of looking and representing everything we observe around us. Mm-hmm. It's useful in a sense it unifies all of the branches that seem to be disconnected before, like physics, biology, maybe psychology, sociology, whatever you want, right? So it provides this unified framework, yet it is still a model. Now, however, we can try to push our luck a little further and say, well, maybe that's the way how the universe works. It isn't just a model. It is not just a convenient way of doing the calculations, but this is how the universe is defined. This is really the theory of everything. And then there's a danger to go this way, because it's obviously too speculative to say for sure. There are many phenomena that hadn't been yet explored in the context of the theory, but there is a possibility for them. So if I'm to bet money right now, I wouldn't say it is 100% guaranteed to be the how the universe works, but there is a pretty good chance that might be.
Now, let's get into some of the nuts and bolts here. Now, to understand this neural network model, perhaps you should explain for us this distinction between the fast-changing non-trainable variables, in other words, the states of these neurons, and the slow-changing trainable variables, in other words, their weights and biases. Now, can you unpack these two, because they are essential to the maths, aren't they?
Oh, absolutely. Yeah. So they're essential to the math, and they're also essential to the generalization of physics that I'm trying to bring. So we can think that this non-trainable variables that are just states of neurons, as you said, in artificial neural network, or even in standard physics, they're just the state of the system, like position and velocity of a particle, or many particles. And then they're stupid in a way that they just keep changing according to rules that are given to them. So in physics, that would be a standard model Lagrangian, say, if you go to the very high energies. or Newton's law, or the Maxwell equation. It's stupid in a way. You know the state, you know the law, and it keeps evolving. There's nothing that needs to be trained. And this is the way it is. And then we have a question: why is this law, and why not some other law? Why is this Lagrangian of the standard model, or not something else? So this question we cannot ask. And that's what non-trainable variables are. But now imagine that we have the new type of variables, and when they change, they actually modify the law. They modify the actual laws of physics. Now, very strange. That's not something we are used in physics. There are some regimes where something similar happens in physics, mostly including gravity, but usually in the everyday work that we do, we assume that their laws are fixed, but just unknown to us completely yet. And so our job is to find those laws, and then maybe some philosopher, somebody else will answer, or maybe anthropic principle will answer why this laws and not something else. Now, but with those new type of variables, trainable variables that undergo this new type of dynamics, the learning dynamics, we have a much more interesting view on the dynamics. Now, they can actually adjust and change our laws of physics, and maybe we can observe their dynamics as well. And if we can, then that actually modifies of how we perceive and view physics. So I would say that the presence of those trainable variables, like weights and biases, you said, are well known in machine learning. They are also pretty well known in biology, although we don't call them as a trainable variables. Your genotype, right? So this is something that the organisms evolve and change, and then those variables stay in the future generations. But that is something we didn't have in physics. And so the addition of those trainable degrees of freedom might have been that link of having a theory that now enables us to do both. Physics, machine learning, physics, biology, and maybe beyond, like I said, psychology, sociology. Those are the other things that we are actively discussing with people in the respective areas, and it seems that new ingredient, the trainable variables, gives us the necessary freedom to actually explore those topics and actually make those branches more scientific, like would have more mathematics in it, more of physicist-like approach to those branches.
And it seems fairly logical that if the theory of evolution, possibly the most believed and agreed with theory in the history of science, is about adaptable change, that for that to be lacking from physics seems like a massive gaping hole, doesn't it? What a powerful idea. And it's powerful precisely because it can help bridge the gaps between some of these biggest problems in physics, like quantum gravity, like the emergence of space-time. But before we get into this new type of computer that you're designing for this work, let's establish the way your model can solve some of these problems. Mm-hmm. Now, you propose that the trainable variables you've just been describing in the neural network can be associated with, shall we say, the old physics, the large-scale gravitational equations of Einstein, and then these new non-trainable variables with the microscopic quantum mechanical equations. Yeah. And this gives us a new possible unifying principle between these two, until now, unreconciled theories in modern physics, general relativity and quantum mechanics, and thus a route to the holy grail, the big one. Yeah. A genuine theory of everything, a theory of quantum gravity, right? Now, how have you associated these totally different equations to each of these variables? How do you do that? And then how does the neural network provide the bridge?
Yeah. So first of all, I wouldn't just put it on one side trainable and the other one in non-trainable. They really work together. And if they were decoupled, like, and here we only have non-trainable and here we only have trainable, then it would actually be easy to solve. When I'm saying let's monitor trainable variables, it means that I still have non-trainable variables, but I coarse grain over them. I integrate them out. I kind of put them under the rug in a sense that only keep few parameters about them. They're still there, and their dynamics is still important. And then I only concentrate on, say, trainable variables. And then I look at their dynamics, given that there is still those untrainable variables, there's still a coupling between them. And I study the equations under which they evolve. They're usually some kind of stochastic equation, like random walk, Brownian motion type dynamics. But in addition, they have something.
Stochastic for the listeners. What's stochastic?
Oh, like Brownian motion, like random walk. You have a very drunk person on the street, and you have
chaotic, unpredictable.
Chaotic, but in a certain way, right? So they're like, if you find a drunk person on the street, then it is chaotic, but given where he started, you can construct a distribution probabilities of where he will end up, and so you can predict probabilities, but not precise location of such a particle. And so you can view them this way, but their dynamics is a bit more complex than that. And the reason it's more complex than that is because of there are this other non-trainable variables that I've integrated out, put aside, but still I know they are there, and so there is still effect of them on the dynamics of the trainable variables. And so when you do that, when you actually keep in mind that there is something from the non-trainable variables, then the dynamics that you get for equations is not stochastic, it's not just random walk, it's not just drunk person, but something more interesting. And you get some different equation, and that equation very close to quantum mechanics, but isn't quite quantum mechanics yet. But this is something that suggests you might be on the right track. Maybe eventually you will derive quantum mechanics. And so then that final step towards deriving quantum mechanics was a very simple observation, is that if you do have those non-trainable variables, but their number of those variables is not fixed, it can fluctuate. There is the neurons can be created and destroyed. You can have a neurogenesis, or neurodegeneration, right? You can produce them or remove them. If you do have that phenomena, then it turns out the equations that were stochastic, that had those Brownian motion, turn out into something more interesting, and it is exactly the Schrodinger equation.
No way.
And that was interesting, and that was interesting that you wouldn't get it by itself, but you will get it when you have this ensemble of neurons which can be added or removed.
A quick aside, Vitaly.
Right.
Yeah, the listeners possibly don't know how this feels when you spend your life crunching out equations. What did you do when that came out? What did you do? Like, what did you dance on the table? Yeah. Did you run around the block? What did you do out of curiosity?
You have you have some. It's hard to explain. There is something shakes in your body. You're like,
right.
Oh, yeah, you might be into something. But of course, after now, as a scientist, you go through this stage many times, and 99 out of 100%, then you find error. Okay, and that's why you never get your hopes too much up, and then usually like, it looks like Schrodinger, but tomorrow when I have a good night's sleep, I'll discover an error, and then it turn out to be not the one. So it did happen this time. So it's actually more than a year, almost 2 years since we got this result, and so it feels like it is maybe real. Okay. Now, the other thing is important, that what you do get, Schrodinger equation, meaning quantum mechanics, it isn't exact. And so there might be deviation from the Schrodinger dynamics. And we physicists actually like to see deviations from the theory, because that means you push it further. Like when Einstein wrote his equations, if he would have just derived Newtonian equation, that would have been boring. You had the very well working Newton equations, and now all of a sudden you come up with this complicated tensor calculus for what? And there is nothing new. So of course, the hope is that you do get something beyond, and that was exactly the case here. There's something beyond quantum that you will get. But the other important thing that it's also up to the neural network to adjust its parameters if it wants to be quantum. So it could have adjusted it the wrong way and say, well, no, I'm learning and I'm happy the way I am, and I don't want to be quantum, approximate quantum. And then maybe that would have been more efficient for the neural network because, or maybe not. It turns out the neural network of the world actually adjusted its parameter on the micro scales such that it is behaving as a Schrodinger. And so that's also interesting.
Are we speaking about a real intrinsic connection, or is this purely a mathematical connection?
Yeah, again, model versus that's how it really works. So when you develop a model, you make an assumption that that's how things work, and you see whether it agrees with the experiment. Now, is it correct? Is it this really how the universe works? Or maybe it's just an approximation to some other even deeper theory? That we don't know yet. But we do make this assumption. So in all of the 19th century, let's say we made an assumption that the fundamental objects are particles. And that was an assumption, right? We didn't have a proof of that. But given that assumption, you derive certain things. Then we thought maybe fields is a better description. And you make this assumption, you make derivations. And again, this is just a model, but maybe it is how the universe works. Well, it turned out not to work very well with gravity. And so we went to strings and say, well, maybe the strings are the fundamental ones. And then let's see when you can get gravity out of it. Didn't work as well. So here we're just making this one assumption. Well, the fundamental objects are neurons, not particles. Yeah.
Have you, I'm sure your excitement and the fact that these equations are fitting together in a way that quantum gravity really hasn't been able to achieve until now, after a lot of trying, presumably a lot of your colleagues started immediately thinking of experiments that could help to confirm this. What kind of experiment, parsimonious, something simple could be done to confirm it?
Yeah, one I already mentioned, that the quantum isn't exact. So it doesn't even have to do with gravity for now. So I haven't told you about the side of the gravity yet, but let me just concentrate on quantum mechanics. It isn't exact, and so we should see violations of it. So there should be certain states that would not quite evolve for quantum mechanics. Maybe this will actually put a limits to what this to build quantum computer can do. And so maybe we cannot do just because this simple thing will not be exactly quantum. And so that is one of the experiments which is underway right now. So maybe I'll do calculations and I'll figure out, oh no, you cannot build a computer beyond certain number of quantum bits, regardless of how much money you invest. So that's one possibility. The other possibility is a lot stronger than that, because this paradigm says that everything is learning. And some things can be already close to the learning equilibrium and learn very well. Other things may just continue learning.
Vitaly, learning equilibrium. This is a machine learning term.
Right. Haven't quite said that yet. So when you train, say, machine learning system, a neural network, and you observe how its loss function, how its performance changes with time, it usually decays very fast, and it learns very fast in the beginning, then it slows down, and eventually gets to the state where, the weights and biases are kicked around and they change their values, but the overall performance doesn't change. And that state is when things do change some microscope, but the macroscopic parameters don't change. We call it equilibrium. So we all know about this equilibrium in thermodynamics, regular thermodynamics. You have a warm water and you have a piece of ice. You put a piece of ice into the warm water. It slightly cools the water, but then eventually this whole system, ice, and then the water come into the equilibrium. They're all at the same temperature. And it stays there for a very long time, and it can stay there. So something similar happens in machine learning, and something similar happens also in this theory of the world as a neural network. Now, we're not there yet. So the entire world is still actively learning. And so we're not close to the learning equilibrium as the universe. But some of its parts do get to the equilibrium. And the smaller the part is, the faster it can get to the equilibrium. And that is the reason why when we actually study the smallest things in physics, like atoms, molecules, or smaller particles, they're small. So they came to equilibrium fast. And the learning dynamics for them basically doesn't matter much. And so that's what the learning equilibrium is. Now I forgot what I was talking about.
Well, thank you for the clarification. It was in the context. It was in the context of an experiment that could confirm.
Right. So now, as I said, so one is the deviation from quantum mechanics, but the claim here that this happens everywhere on all scales. You have learning dynamics, and learning dynamics has one very distinct feature from the regular physical dynamics. And that is a violation of the second law of thermodynamics as we know it. So the second law tells you if you have a system and you just leave it for a while, its entropy will grow, right? We all know if you don't do anything in the house, then it becomes a mess, right? So, everything, especially with kids, there's lots of entropy going on. And now, the second, the learning does something different to it. It actually tries not to increase the entropy, but to decrease the entropy. It tries to, now when we look around us, we as a subsystem, we are trying to interpret the world around us. We are trying to predict the world us. We are correlating the degrees of freedom outside of us to degrees of freedom inside of us, inside the brain. And that correlation decreases the entropy. So once you do put into the system those biological organisms like humans, or even cells or some viruses, whatever it is, they behave differently. They behave differently according to physics laws. And that's why the other place of testing all those theories is actually at the border between physics and biology, where you start to deal with a more complex system, like longer molecules, maybe organic molecules. And there, the dynamics that you would predict from just pure thermodynamics would change. And so that is why right now we are exploring many biological experiments and seeing, okay, maybe there you can actually there's a lot to be explained. There's a lot of biological data, even take coronavirus data, that you can just take that data and try to see how this learning paradigm explains the state of the system, when the new variants of virus will arrive, having kind of early warning signal in the data. Watch out, the new variant is coming, and then you need to do that. So at the level between biology and physics, there is a lot to it. And now moving to larger and larger scales, so even on the cosmological scales, the gravity, that is the emergent gravity that is derived from this theory, when you now keep track other way around. So for the quantum, you would keeping track of the trainable variables and integrating out of non-trainable, like putting them under the rock. For the large scales, you know that the system is very far away from equilibrium, so you cannot just integrate out and remove the non-trainable variables, and so you have to keep track of them exactly. And when you do that, you get different dynamics, different equations of motions, and different things emerge, like Lorentz invariance, space-time. I'm not going to use the Lorentz invariance. The space-time emerges, and that is another place. It does emerge. There is gravity, there are Einstein equations, but they again approximate. They will again break down. And if they do break down, let's calculate predictions how they break down. Is their breakdown just the dark matter, what we call the dark matter? We can just associate with the breaking down of the Einstein equation. And if that's correct, then here it is, a confirmation of the theory. Coming from the large-scale experiments where we know that the system. Another place where general relativity doesn't work quite well is their early universe, and you have to put in something new. You have to put in inflation, cosmic inflation, in order to explain certain things. So once again, can you explain that within the context of the theory? And so there are many places like that, dark matter, even dark energy, cosmic inflations, where let's calculate precise predictions from the modifications of general relativity or Einstein equations and see whether they match what we actually observe. So there's a lot. So I took you from the smallest scale where quantum mechanics would have to be modified to the boundary between physics and biology, where we should see this entropy decay and not production. That's interesting. And then the third place is the universe. It's the large scales where dark energy, dark matter, cosmic inflation are all the playgrounds for us to test the theory.
But it's interesting hearing you talking about learning as a sort of an opposite to entropy, because obviously the accruing of knowledge and efficiency is exactly the opposite of that. Would you say that as that heads towards a learning equilibrium slowly, somewhere else in the universe, we would see an increase in entropy to balance that out? Or do you think that's a sort of old-fashioned way of looking at it?
It is old-fashioned. So I think it's old-fashioned. I think entropy is a lot richer parameter that we want it to be. And it's not just one number in the universe. It is something that you can measure locally. So there is entropy density here, entropy density there. And just saying, well, but the whole universe, maybe entropy is increasing, is very little. It's very little for us to say. There's a lot more data of the entropy dynamics, information dynamics that's going on. Now, but the one place I can point out to people to think about, so it is true that in the room, if you start with the molecules in the corner, they'll fly all over the place and kind of entropy will increase. But if those particles are in the universe and they're just gravitating according to even Newton's equations, they will not do that. They will cluster, okay? And that is effectively is what entropy decay is. They don't want to explore all of the phase space. They want to cluster together. They want to clump together. And so that's kind of a high school intuitive way of seeing that maybe that dynamics on the larger scales isn't really increasing the entropy, that does something smarter. Now, of course, now this is just a Newtonian picture that high schoolers would have to go to the entropy described through the entropy production described on large scales, and to arrive into the Einstein equation, you have to follow a few steps in the derivation. But at the end of the day, I think that is the main message, that do not think of the entropy as some stupid thing that always grows, but there are interesting places when it decays. And in fact, if your system is dominated by learning, it is the opposite to the second law that is happening. We can observe it in the numerical simulations of the artificial neural network. We can just plot the entropy and see it goes down. So I think this is just a mistake we made, and as physicists, it was okay because for not much of the learning was happening. Small systems are all in equilibrium. And so not much effect from the learning dynamics. But as you go in the larger and larger scale, the effect of this decrease of entropy due to learning becomes more and more pronounced. And the boundary is exactly from physics to biology, where you say, well, hold on, there is no way now I can explain the origin of life just with the chance or with the physics. People know that. They try to say, well, maybe just random arrangement of molecules created the first self-reproducing organism or whatever it was. But the numbers don't add up. So the chance isn't quite enough to have the life to emerge. And so I've worked with a biologist, and that's why I spent 2 years, almost 2 years, year and a half, NIH, working exactly on that, saying, all right, how can we take this theory of neural networks and apply it to biology, to evolution? Can we, out of that, then get answer on the question of origin of life, where it would not just be a chance, but would be something that had to have happened, right? So there is no chance to not get the life just in a system that wants to learn.
Does this take us towards an understanding of the fine tuning, or is that a separate question?
Yeah. That's what I was going to say next. Because now, without it, without this learning dynamics, you have to answer two questions: why do we observe the laws of physics we observe, and why we actually are observers in the universe with those laws of physics? And then it arrives you to the anthropic-like reasoning. Well, in other universes, observers would not form, and so they wouldn't be able to observe it. And here we come to anthropic reasoning. And that is okay, but it's not the prettiest of all. Here, instead of saying, and then you say, yes, constant, I just fine-tune for life, and that's it. Now, who fine-tuned it and what the process of fine-tuning is not specified. And then people argued that maybe, well, there is a landscape of all universes. There is a landscape of string theory of vacuum, and then only in those places that are consistent with life, observers will emerge. There's still a problem, because you can perfectly well have a universe which is consistent of life, but the life still hadn't emerged because it's a random chance of putting together a large collection of molecules that will assemble a first organism that can start replicating and evolving. So that doesn't quite fix the problem. Now, the answer with respect to learning theory is, I think, much more elegant than you say. It doesn't matter with which universe you started. It undergoes learning evolution. It tries to come up with, it learns itself, basically, because there's nothing outside to this universe. The left side of the neural network learns the right side of the neural network. Every part of it learns the rest. And it does that. And then eventually it is to the advantage of the neural network in terms of algorithms to produce this information processing units. So at the smallest scale, those information processing units are neurons. But then on the larger scales, and we observe it in machine learning, they create like subnetworks, and then subnetworks of subnetworks. And then on the smaller scales, they're all neurons, but once you go to higher scales, there may be particles, elementary particles. We call them particles, but they're actually networks, small networks of neurons which are connected in a certain way. They've trained their variables in a certain way, so they're very good in identifying maybe location of other particles of themselves, and so they know how to exchange information. And then you go to larger and larger scales, and it's not surprising that this whole hierarchy forms. This hierarchy is expected to form if we just blindly run machine learning algorithms. You see the many different scales appearing, and this is what we call self-organized criticality. There's many fractal-like structure appears in the neural networks. And so in the fine-tuned universe, you still have to answer a question: who fine-tunes it? Why there is this landscape on vacuum? And even when it's fine-tuned and you have landscape in vacuum, how do you make actually observers emerge there? And numbers just don't add up. You don't get high enough probabilities for cells, organisms to emerge. Now, in this case, you don't have any of that. You have a system, a neural network that has to decide itself which laws of physics, so to say, it will create, because those laws of physics will enable it to better learn itself. And then it will continue this evolution, and there it will necessarily form some kind of physics first, then some kind of chemistry first, and then some kind of biology next. And then after biology, some multicellular organisms, and then societies will form, etc. So this is just a useful way for learning, right? So and now we observers, maybe the largest observers, at least in our part, we are capable of understanding and learning the environment around us much better than individual cells. And that's just a result of the whole universe learning and undergoing through this phase transitions.
Is there a connection here with the idea in human neural networks of neuroplasticity? Because it seems to me that this extremely dynamic adaptability of neurons in the brain, it could quite simply work like that in the universe as well. When we see this fine-tuning taking place to raise efficiency, to increase I guess efficiency is the word I'm looking for. It just becomes it becomes more efficient. It becomes losing less energy in the process, reducing entropy. Is there a connection between the idea of neuroplasticity and the fine-tuning for life?
Yeah. So first of all, you mentioned efficiency, and again, we are increasing efficiency of the neural network, and I think this is increasing the consciousness. So now we have collective consciousness that as well. So I just wanted to comment on that quickly. But coming back to the plasticity is essential for this microscopic neural network to work. Plasticity is nothing but weights get reconnected. The weight matrix evolves and lives. Every neuron can, in principle, get connected to any other neurons. And the prediction of this that we all connected. You have atoms in your body, I have in mine, and they're all neurons, and there are connections. They can be strong connections or weak connections, but those connections are everywhere. And the plasticity at the level of those microscopic neurons is just the ability to change those connections, and that is absolutely essential for learning. It is absolutely effective for learning on all scales, including the smallest microscopic scales of where the given laws of physics emerged.
But you're suggesting a collective consciousness is somehow behind that adapting process.
Yeah. So consciousness is collective consciousness is in my definition is this large one neural network that was pretty stupid maybe in the beginning, but then through learning and through developing a more efficient connections, increased its consciousness, and now it's much better in learning. Learning the environment, learning itself, basically. It is a collective consciousness, but yet this learning happens on all scales. Not there is one scale, as you said, the whole network, it's a collective one. There is a scale of the populations of biosphere. There is a scale of the group of organisms, like, human beings. There's a scale of the individual cells. There is a scales of atoms, and all those scales, you have the very same phenomena of learning and making it more efficient. The smallest scale tells us what the most efficient way of exchanging information between individual neurons, but in larger scales, what is the most efficient way of exchanging information, let's say, between humans, right? So we could have communicated through sound only without light, but that wouldn't be very efficient, and we would have not evolved as fast as we did. And with this extra communications through light, we acquire a lot more information that enables us to learn faster, communicate our ideas and so we are always, and that is neuroplasticity, deciding which communication channels we should use. And so that plasticity is essential on all scales, from the microscopic to the microscopic. It is only what we call plasticity changes its roles. On the microscopic, it's really individual neurons, microneurons. On the larger scales, it's something else. So maybe, the social networking, right? We have social networks, and there's still connections between people, and those social networks change. Right? Today, I speak more with my, family. Before, I spoke more with my friends. So I'm reconnecting, trying to adjust. Maybe, now I'm speaking with you, so we're establishing connection between us. And that's plasticity. We didn't have that connection, a month ago, but now we do have that. And that seems to be beneficial for the performance of this whole social network. And so we do that. And that is plasticity on that scale. And the same happens in our head, right? So neurons figure out, I want to connect to that neuron because it gives me some information that will make my dynamics as a neuron better. Yeah.
So just to wrap up on quantum mechanics, you mentioned the evolution of observers coming out of this long evolution.
Mm-hmm.
What can your theory do to get around some of the observer problem? The measurement problem is the way it's called in quantum mechanics. This issue of a macrocosmic system interfering with the quantum system. What does your theory do to kind of put to bed? Yeah, to shed light to put to bed this issue.
Right. So first of all, there are few interpretations of quantum mechanics, but the two ones that I was mostly interested in. One was many worlds interpretation, and the other one was Bohmian interpretation, or hidden variables interpretation of quantum mechanics. And I was always not satisfied with the many worlds interpretation it was beautiful and everything, but there were no probabilities built in there. So it was a problem of how to actually put observers there and make observers observe things with certain probabilities. So that was problematic. Now, hidden variable theory was all great, but it was not clear what are those hidden variables. What is their dynamics? When are they present and when they are not present? How can maybe I learn those hidden variables and then get rid of the quantum mechanics? And I thought it was always that was important to realize what the right interpretation is, even before we start tackling the problem of measurements and bringing in the observer. Well, it turned out I was wrong, because now we get both. We get the observer and the quantum system. They're following the very same rules. So observer is collection of neurons trying to optimize and learn, and the quantum system tries to optimize and learn. The only difference between the two, the quantum system is in the learning equilibrium. So it's learned everything it could. It doesn't get any more information to make it better than it was. And on the other hand, observer is very far from equilibrium. It wants to learn the system and wants to open the box and see whether the Schrodinger cat is dead or alive. But I wasn't able to do until I realized what those hidden variables were. And those hidden variables are actually those non-trainable variables that I was talking about in the beginning. And the fact that we are not measuring all of them simultaneously makes this the system quantum, but it really isn't. It is really statistical system. It's really just our not knowing what those variables are tells us that the best way for us to do calculations is to use the Schrodinger equation. So it's kind of, we made too much of a deal out of the equation and made it macroscopic and said everything is just a wave function. Yet it was just it just was a state of the system that figured out that it's convenient for this subsystem to learn using the laws of Schrodinger dynamics in equilibrium. And then the question is, yes, so I think this puts to rest the problem once we do see the deviations from the quantum mechanics that I mentioned. And then you will see, okay, it's deviated, and in principle, I can really find all those hidden variables. And then there is no issue in measurements. And the reason why I don't know outcomes of the measurements is just because I don't know those hidden variables. And if I knew, then the particle in a double slit experiment wouldn't go through one to another. It would actually go through only one of the slits. And so that's kind of would put it to rest. But again, this one step needs to be done. We need to come up with a clever experiment, which is well isolated, very small, where we can actually identify and see the deviations from the Schrodinger design, from quantum mechanics.
You're the first physicist I've ever heard speaking so comfortably about these variances from these extremely hard worked out equations that everybody goes on so much about how accurate they are and how brilliant they are at predicting the universe. It seems I don't think I've ever come across a physicist who was actually not only comfortable, but actually welcomed variances from this as if it was a natural evolution for the future of science. I really agree with you there. That's a wonderful humility, and also a certain kind of honesty about the fact that these concepts are always only mental constructs and mathematical constructs. How do you find peace with that? Is it a love of the unknown that makes you feel so comfortable with that?
Oh, absolutely. I mean, that's why I'm a physicist, right? So there's too many things that I don't know around me, starting from the age of 8, like you said, right? Starting from the question about infinity and what it is, and I want to know what it is. I'm trying to figure out what it is. But the approach I take is that nothing is written in stone, right? So the all laws, whatever they are, even the second law of thermodynamics may eventually get violated. And so we should not trust it blindly, but actually see what interesting phenomena will bring to us if they are to be violated. I think that's what actually most physicists do with most of the theories. However, quantum mechanics was very strange, and people just took it too literally, I think. So they decided, okay, we'll give up and we'll allow general relativity not to be precise. We'll allow Maxwell equations not to be precise. We'll allow all of the new fields to appear, but don't touch quantum mechanics. That was kind of the approach for the last, 40, 50 years. Don't mess with quantum mechanics. Very few people actually are trying to say, well, maybe quantum mechanics isn't, there are, but not a large number. They're saying, well, maybe quantum mechanics isn't exact. Maybe it's also emergent. So one of the well-known people physicists who does that, Hooft, and he's one of the proponents of the idea that maybe quantum mechanics isn't quite exact, and maybe it is an emergent phenomena. But there is a very strong opposition to such view. Let me put it in soft terms, but I'm okay with that.
Yeah, and this idea of a certain variance and an evolution, it fits with your trainable variables idea that really there's a lot of room for change, and there's a lot of room for variation here. Okay, Vitaly, I'm going to move on now. So in the last few years, as you said earlier, you've moved from your long-term position at the University of Minnesota. You've joined the NIH, the National Institute of Health. And at the same time, more or less, you've launched a new company, Artificial Neural Computing, the link for which will be in the show notes, listeners, if you want to go and check out this new venture. And it's using all this theory to look deeper into the nature of reality, not only by modeling neural networks using machine learning, but also by modeling evolution in biological systems. And this is a connection that I've been wanting to talk about on the show for a while, because it's just useful in so many ways to use computer simulations to model nature's complex workings, which is what science is trying to do. So first of all, Vitaly, tell us about this new artificial neural computing project and how it relates to the new computer and the new computer processor that you're creating for this work.
Right. The reason I started this venture is because there is a unique opportunity for us to explore how the nature works at the interfaces of things we didn't think had anything in common. So the one is physics and biology. Physicists always work on their own stuff, biologists work on their own stuff, and there was very little interactions and collaborations between the two communities. So that is one thing that should be erased. So I think now with this neural network theory, there is a common language. There is a common language in which we can talk, and that venture is about that. Let's bring everybody with all the different skills under one umbrella where we can discuss those ideas, given them the theory. Now, I only mentioned for now within the company only physics and biology, but potentially all others, right? Psychology, the sociology, everything that goes on the larger scales can also potentially benefit from constructing coherent theories. Business as well, constructing coherent theories within the construct of the theory. But now let's go to the machine learning, because machine learning was the heart of it. The whole theory started from the mathematics of machine learning. And so we have all those beautiful theories, physics, biology, etc. And nature worked very hard for billions of years to come up with the most efficient algorithms for learning at the smallest scale, which we now call physics, for learning at a bit larger scale, which we now call biology, etc. So the nature had done all that hard work. If the concept of the world as a network is correct, then the nature had done all this work. It tried all different algorithms. It's had tried and failed for some, and then others it kept. So why not just borrow it from them? Let's not look what the biology does, look at the biological phenomena, and see, well, what is it? Is it useful for machine learning algorithms? Can I take a given biological phenomena and then encode it in my machine learning algorithms? And then my Tesla cars will stop crashing and actually will drive better, or my speech recognition will be more perfect, even if I have Russian accent, right? Is that possible? Right? Can you actually do that? And that was something that I wanted to try first, and I tried it, and I saw that there is so much potential there. There are really a lot of algorithms that nature discovered. For example, the replication algorithm. There's something that nature does all the time. There is a replication on all scales. Their cells replicate, the multicellular organisms replicate. Can we incorporate it into the machine learning, and maybe it will benefit? The program death, also another biological algorithm that can be implemented. And I already mentioned, when you actually do allow creation of new neurons, replication, and destruction of neurons, that is essential for quantumness. And so maybe once we take that and put it in the algorithm, it will have emergent quantumness, not the true quantum, but emergent quantumness. And if that's correct, then you can have a completely classical computer on which a clever machine learning algorithm runs, and as a result, it produces emergent quantumness. It behaves according to the Schrodinger equation. If so, here it is. Here is your quantum computer. Not the true quantum computer, but the emergent quantum computer. Not the quantumness of the fundamental physical level, but the quantumness on the levels on which your neurons are created in the memory. And if that's correct, then here it is. You have borrowed the algorithms that nature worked so hard to develop, and you just installed it in your PC. And that's one way dynamics. But you can also think about doing it the other way around. You can test certain algorithm that you just cook up yourself, see its advantage, and see, well, why nature didn't figure out that? Let's go look for it. And so, and by doing that, you have an algorithmic prediction of what the nature should have discovered if it was clever enough. And if it didn't, let's figure out why. And so that collaboration between all this physics and biology skills and machine learning skills, it works both ways. And it helps us to better understand how physics and biology works, and it helps us to build better algorithms.
So you're saying that it's not a quantum computer in the technological sense of the way quantum computers are now being created. By the way, listeners, in this series, we're speaking with Shahini Ghazini from, I think it's from Toronto University, where she's going to be explaining how quantum computers work. But what you're saying here is that you've designed a processor that is learning in itself, and it may actually have emergent quantumness come out of it. Exactly. How long do you think it would take before you would see
3 years. That 3 years, we are now on track, but we just started, so we'll see. So, but the idea is exactly that. So we're creating a processor that actually only job is to do learning well. It will be horrible in adding, subtracting large numbers and doing, multiplications. It will be exactly as dumb as we are with respect to the, arithmetics. But it will be good in recognizing patterns, right? Doing exactly what we do well, because we have exactly the same architecture. And if that's correct, then this is it, right? So then we'll have a computer that, first of all, will do learning very well, efficiently. So it wouldn't be using the processor and the computer architecture that we are using right now. This computer architecture was not designed for learning. This computer architecture we're using now was designed for exactly, multiplying, adding large numbers, for doing some arithmetics. The other computer will be horrible in arithmetics. It will always produce results, but it will be good in one thing, learning. It will be very good in producing. And then, if it is good in learning, and if it does do well, and then you can imagine such a computer would be useful anywhere, because it would consume a lot less power than the normal computer. It would be happening everything on the molecular scale, all the learning. And if it does do that, then we say, all right, well, let's use the concept of emergent quantumness, exactly what you said. And then let's not only use it as a learner, as a robot that knows how to navigate in the complex environment, or as a self-driving car. We'll use it for something else. We'll use it for something which I think a lot more interesting, for the emergent quantumness. And then we'll use this concept. We'll adjust its learnable trainable parameters in such a way so that the true Schrodinger equation is produced. So you have to have this ability of adjusting that. And then you are in business. Then we have an actual emergent quantum computer, not only a neural computer, which is like almost guaranteed to happen in 2 or 3 years from now, that will outbeat all the digital computers, but actually also a quantum computer that can do something in addition to that, some kind of computation. Signal here, the warning sign is that it is going to be approximate quantumness. And so it is yet for us to see what kind of quantum speedups it can get, for what kind of quantum computational task we can get of speedups, and for others, maybe not. So I'm always thinking this quantumness as a possible byproduct of the research. One is the guaranteed thing, is there's a neural computer that sometimes people call it a neuromorphic computer, so it have this neural processor, only good for learning, but as a byproduct, would be very interesting to see if we can have emergent quantum.
This is such a specialist terminology. I have to ask you, Vitaly, what exactly are you talking about when you talk about emergent quantumness? What is it that you're hoping will emerge?
Right. So remember I told you that the quantum mechanics emerges from the neural network at the smallest scales, if you keep track of the trainable variables. So that happens on the smallest scales, and we do see their quantum mechanics. Now, we realize now a more macroscopic architecture where the same learning dynamic happens. Our brain is one example, of course, but we are building a processor where the learning will happen. There'll be a degrees of freedom. There'll be like weights and biases. There'll be a degree of freedom, like state of neurons. They will have all that. And then this material, this processor is learning. But if it's learning, so is the microscopic material of the world. And if we saw quantumness there, and if that's correct, why not here? And then, and that will be more controllable quantum behavior. So basically, we're just saying, like, if this learning dynamics is correct on all scales, the people who are building quantum computers, they're building it there on the microscopic scales, where we do know what quantumness is, but we have less control of how to make it pure, how to come up with the right Hamiltonian. But here we'll have more control. It will be right here at the scales of the more macroscopic scales. And if it is true that it emerges, then here we go. Let's create on that scale, on the scale where we have everything available, but using the very same phenomena that's happening down there on the microscopic scales.
And listeners, we must draw attention to the fact that this is really quite controversial, because really one of the biggest problems that we found in sort of quantizing up to the classical level is this problem that when we get larger scales, the quantum calculations just break down. So this really could be an extraordinary discovery if it turns out to be true, and how wonderful to actually have a physical computer in the physical world that we can actually monitor to see if this can actually happen and it's not just theoretical. So wow, what an exciting experiment. Good luck with that one, Vitaly.
Thank you.
What other applications can this kind of neural network simulation model in the future? You mentioned just there that we're within 2 or 3 years of a neural based computer. But just to get a sense of why everybody's investing in this so heavily at the moment, what are the applications if we can really nail this?
Well, in terms of investing, it's a very small percentage of investment to the neural neuromorphic computing versus quantum. So there's a heavy investment in the quantum computing, and that is maybe an oversell. And I think that we are decades away from that true quantum computer. So this one is not as heavily invested. Usually invested as under umbrella of neuromorphic materials, and there are some big companies that do research on that.
Sorry, Vitaly, neuromorphic materials?
Yeah, neuromorphic materials is the material that would actually have the features of the neural systems like we know, like our brain. So that's what they call those materials. Materials that have
artificial biological substances.
It's recreating the biological systems like we know at the scales of the physical systems, at the scale of material science. People do that for different purposes, like as a memory storage device. Here we are taking it's one step further. We don't want this neurocomputer to just be a storage device of data, digital data. We want it actually to have this ability to learn. And so the neuroplasticity that you mentioned is essential for that material. So it has absolutely to have that plasticity of switching, the molecules, the bonds, and it has to be. So put in a perspective, something like crystal would be a horrible neuromorphic material because just frozen in a given state, there is no plasticity. If you take some, gas or fluid, it's too plastic, meaning it quickly switches, molecules float around and they never get stuck anywhere. So you need something in between, some material that actually neither crystal nor fluid. So and there are some materials like that, like phase-changing materials that can have both the plasticity and also percolation through the entire sample. But this area is not as heavily invested as what we should probably be. But I think if we are thinking of sending robots to the Mars, then I don't think we can just send our digital computers. That would consume too much power to have these robots to learn anything or how to navigate environment. You have to be really compact in the energy usage of such computers, and so that they can learn efficiently and at the same time consume less power. And that is, but there are, of course, the applications of the computer are everywhere. And the idea is to make this material not just for one simple device, but make it scalable, right? So if I want to have a bigger head, I cannot do that. I cannot afford to make my head, 10 times bigger. But with a computer device, maybe with the material, I can just blow it up and put more material, make the processor bigger. So maybe the scalability is an important issue in making this. But yeah, it is not as heavily invested as I would think. Because too much investment now went towards quantum computing. And I think if you compare what are the chances that we'll have a quantum computer within 10 years versus what are the chances that we'll have a neural computer in 10 years, I think there's neural computer is definitely a winner, and despite of the fact that there's much less money invested into that.
And this idea of sort of modeling digitally the human neural connectome, I was interested in how, in your opinion, this relates to the development of human similar AGI. Are there any implications from your work, from your research, from this particular processor, or from your theory for the future of AI and machine learning in that sense?
Sure. So first of all, I don't think this processor will be digital. So digital is something that we use for devices that we communicate with, where it is important to actually not make large mistakes. And I said, adding numbers, subtracting numbers, you have to kind of be sure that you will produce the same result if you do it twice. It's more analog. So it's more analog, whether there's not just zeros and ones, there is a continuum of variables that you can take. So I think it will be more of an analog. And it looks like it will be easy to scale. So the preliminary results that we have, it will be easy to scale. And then that's it. If you can scale it, then as I said, making the brain twice as large, 10 times as large, 100 times as large will be just the matter of just putting more things together. And if that's the case, then yeah, we can get a computer that can have a pretty high intelligence. Now, whether it will be as high intelligence for all learning tasks as us, I wouldn't bet on that. But I think it will be certain. It will be doing certain machine learning tasks much better for us than us. So, for example, something like self-driving, and that's one of the things we are working on within the company. I think that problem will be solved.
But even with that distance, it does bring AGI closer, surely.
Right. So yeah. So it will. So certain tasks will be able to do basically right away. So as I said, self-driving. I'm going to bet on that. All these possible recognitions of how to navigate in new environments. Sending robots to Mars, having all the complicated things that even we wouldn't be able to do. Because sometimes we didn't evolve to be good drivers, right? We evolved to be good, maybe walkers, maybe good fighters, maybe good, but not drivers, right? So I would bet then, and you can see it different on the streets that not everyone is a good driver. So I think there will be type of machine learning problems that this system will solve much more efficiently, much faster. But then there'll be others, more creative, that use more levels of learning that actually took us many a very long period of evolution took us to establish the architecture that we currently have. So I don't think we'll be able to match exactly that, like out of the blue, just by creating this computer. So I'm sure that if you have like some creativity tasks, something that revolves writing down new theories in physics or doing more creative work, then I don't think we are anywhere close, and will be close in beating that. But the simple task, I think, will beat them very fast, and so I would say that will be fixed within the next decade, much faster than quantum computing. So I'm very skeptical about the true quantum computer. I'm very optimistic about that idea of emergent quantum computer. So that I think will happen much sooner.
Well, Vitaly, this is so fascinating. I could go on. There's so many things I want to ask about. But I think actually I prefer to bring it to a close with a more philosophical question here. I mentioned the difference between an analogy and a model and these sort of very much conceptual construct questions. And I've got this slightly wacky idea I wanted to run past you, which is that whenever we're modeling nature, using mathematics, using computers, using technology, I come back to the possibility that life itself, that nature itself, could in some sense be a technology. Consciousness could be in some sense a technology. The emergence of life itself, there's this wonderful, very, very controversial idea of biocentrism, the idea that life itself gave birth to space-time and not the other way around. Have you ever had any moments where it seemed to you that biology was in fact a technology rather than technology coming out of biology?
Well, okay, so biology is a technology, but the question, how was it discovered? Was it discovered through some learning phenomena of molecules that first had no biology in it, and then all of a sudden the phase transition took place, and then we end up with some biological organisms? Yes. Whether there was a deliberate construction of some non-biological organism, I know, whatever you want to call it, that decided to, let's create a new type of organism that this organism will call biology. That I don't think so. So I think it's more kind of not a designed way. Not, but by technology, I mean exactly that. Is that you have some evolved organisms, and all of a sudden this evolved organisms create something else that is useful on that scale, like iPhone, right, or the internet. Whether that something like that had happened before us, before the technological age. That I'm not sure, but I cannot dismiss that option either. So it may very well be that there were some primitive organisms, and then they were living there. I don't know, viruses, say they were living there, they're hanging around, and like, okay, well, that's it. We're not evolving further. Would be nice to create something better. And so viruses got together, had some meeting, and they created a cell. And then the cellular evolution took off. Possible? Yes, that's possible. Likely? Probably not. And so I don't think so. I don't think that happened, but I wouldn't dismiss that as a possibility. Now, if we really want to answer that question, whether it's possible versus how it's likely it is, we should actually go to algorithmic discussion. Is it useful? Right? Is it useful to create technology for learning the environment? Because that's what I think the purpose of kind of every organism is, to learn and understand the environment around us. Now, it turns out to be very useful right now. With technology, we are sending satellites, far in deep space. We are creating all the images from the early universe. We are taking pictures of colliding black holes. We are learning the environment. So that technology turned out to be useful for doing exactly what we are supposed to do, learn the environment. Was something like that happening ever before us? That I don't know. I'm sure I'm not answering the question you asked.
No, it's not really. It's certainly not a question you can answer, is it? But it was more an idea of these analogies, of these ways of thinking about things. I'm very interested in this Buddhist idea of a conceptual construct, and how really everything that we ever do and talk about in science is through this window of a construct, whether it be mathematical or linguistic. Right. But there is a physicist who's been on the show by the name of Thomas Campbell, who's famous for his work with out-of-body experiences. And he's got a really radical theory where he's essentially proposing that consciousness divided itself into smaller units, a bit like this idea where you were talking about these smaller and smaller systems with their own units of consciousness, particularly with the objective of reducing entropy, of learning, of becoming more and more efficient. Yeah. And I find this a very, very compelling idea as a substratum, as a sort of pretext for, shall we say, the creation of space-time and all of its, happenings. But I don't really know how to sort of conceptually insert.
No, I think what you're saying makes a lot of sense. So you have like this neural network in the construction of my theory. You have a neural network, everything's connected to everything. Hard to make sense of anything. Can you imagine like all of the, how many 8 billion people start shouting at the same time, right? You will not understand anything, right? So it's not very useful for you to be able to communicate with everyone at every single moment of time. So what's more useful is to actually first, go our separate ways, have our, and then once in a while, come and communicate, have this fewer connections. And I think the same is happening on the network of this neural network. Is basically, it could have started with lots of connections, but it's not very useful for learning. So what is useful is to break apart, first create some emergent space-time. And that space-time you can think as communication channel. So we create this emergent space-time communication channel, and within this channel, well, let's talk now. Let's try to make sense of what we have around now. And then particles form, and the particles understand, okay, well, now let's create more complicated particles, maybe create molecules. Now we can learn even more. We can get more information. We can store more local information. But too bad. We learn this during the lifetime of a molecule before it gets ripped apart, and there's no way to record it anywhere. So that's not very good. And so we come up with an idea of DNA, and so organism, so that you not only learn something during your life, you keep a record of it. It's like a library. You keep a library of the individual cells algorithm. And then, so yes, the idea first, you break everything apart, have very few connections, only emergent space-time, and then you start to create more and more complex things on it. atoms, molecules, cells, multicellular organisms. Now we are at the level of creating this, network of the internet where we're all communicating almost instantly, right? And we can exchange ideas. And that's another phase transition that we created this one network. And we are like a super consciousness. We are like one organism because if we would be able to collaborate more efficiently with each other, I'm sure we'd be able to solve many, many more problems. And actually, with this idea of this creating a company on the intersection of physics, biology, and machine learning is exactly about that. There are people who have strong physics background, biology, machine learning, but not common language. Physicists cannot speak to biologists. Physicists cannot speak to machine learning person, and machine learning doesn't speak well with biologists. And so having this network of people, and my company is actually international, so there are people everywhere in the world. Group is growing, and we have all different backgrounds, and we immediately connect with each other through the internet and exchange ideas and understand in which directions to move. So I think this is internet provides us with all that, the possibility of creating this super intelligence. We just don't use it yet. And part of the problem, we don't have a good common language. And so if this theory that I'm talking about is able to provide that, that's great. So then we can have the same common language, and let's just interpret different ideas. People have wonderful ideas. Many people have ideas, but they do not have the common language of expressing those ideas. And that's one of the other benefits I think this theory can potentially bring. Well, again, I drifted away in my discussion, but
well, and on Chasing Consciousness, we are huge fans of this multidisciplinary thinking. And my listeners are certainly, like myself, really desperate to try and put these pieces together so we can actually get a broader understanding that does, cross over between these different disciplines. And I think that, just to close, the idea that really fascinates me here is this subsystems of conscious learning, of increasing of efficiency, of dropping of entropy. What is so fascinating about your theory is that it brings us a very rational, a non-woo-woo understanding of how all of those subsystems of learning could be put together in a collective consciousness. And the interesting thing would be that it would learn way more, split into those subsections than it would on its own as a single system. That, for me, is very, very powerful. So, listeners, it leaves just for me to thank Vitaly for his time, for his extraordinary ideas. And do please go off and check the website for this extraordinary new company, the Artificial Neural Computing. The website will be in the show notes, and there in the research section, you will find, as I said, all these multidisciplinary papers on a single web page, and you can really start to see how all these things link. Vitaly Vanchurin, thank you so much for being with us.
Thank you.
Wishing you all the very best.
Thank you.